Have you ever watched a shadow outside your window and noticed how its shortest point shifts slightly from day to day? When the shadow shrinks to its absolute minimum length, it marks solar noon, the sun's highest point in the sky. The average time it takes the sun to return to this position is roughly 24 hours. We call this the mean solar day. A strict 24-hour cycle is highly practical for organizing a daily schedule, but it tells you absolutely nothing about when the first winter frost will arrive or when to plant your crops. Measuring the day is only the first step. To predict the seasons and ensure a stable food supply, early humans had to look past the daily motion of the sun and begin mapping the night sky. The most obvious measurable pattern in the night sky is the changing illuminated shape of the moon. The cycle from one completely dark new moon to the next is known as the synodic month. As the moon orbits the Earth, this cycle of illumination takes exactly 29.5 days to complete. That fraction presents a massive mathematical puzzle. You cannot have half a day on a human calendar. To fix this, early lunar calendars simply alternated between months of 29 days and months of 30 days. Over time, that precise alternation perfectly hits an average of 29.5. Absorbing the fraction of the month was a clever mathematical adaptation, but relying strictly on the lunar cycle leaves a calendar completely disconnected from the larger seasonal shifts that dictate agriculture and survival. To track the seasons, we have to track the engine that drives them, Earth's orbit. This split-screen animation shows the Earth moving around the sun on the left and its motion relative to fixed distant stars on the right. The left side tracks the tropical year. This is the exact time it takes the Earth to travel from one spring equinox to the next, completing a full cycle of seasons in about 365.25 days. The right side tracks the sidereal year. This measures Earth's orbit relative to the fixed background stars. Because the Earth's axis slowly wobbles, it actually takes about 20 minutes longer for the planet to physically realign with that distant star pattern than it does to complete a seasonal cycle. Because agriculture relies entirely on the predictable arrival of spring and winter, human calendars must be based on the tropical year of the seasons, rather than the sidereal year of the stars. But choosing the tropical year introduces a massive structural flaw into our timekeeping. The Earth takes 365 days and an extra quarter of a day to complete its seasonal loop. Calendars require whole days. When you have a year that is 365.25 days long, you accumulate a rolling quarter-day error every single year. This calendar grid shows the consequence of ignoring that faction. Spring dates would slide backward into the coldest winter months. The Gregorian calendar solves this by inserting a 29th day into February every 4 years, absorbing the accumulated day. But 365.25 days is actually a slight overestimation of the Earth's orbit. Adding a leap day every 4 years eventually adds too much time, creating an overcorrection. To counter this, leap years are skipped on century years like 1700, 1800, and 1900. They are only kept if the century year is divisible by 400, which is why the year 2000 remained a leap year. Our modern calendar is a highly engineered mathematical hack. It deliberately bends the rules of time to keep human life synced with the actual physical position of the sun. We see the mechanical reality of these different orbital years playing out in Indian cultural festivals. This timeline shows Makar Sankranti, a festival originally tied to the winter solstice. Because it tracks the sidereal year, while our Gregorian calendar tracks the tropical year, the festival steps forward on our calendar by 1 day every 71 years. That 71-year shift is observable proof of the 20-minute difference between the two orbital cycles. Thousands of years before modern apps or orbital mechanics, humans tracked these complex shifts using intricate physical instruments. Checking our phones for the date, planning a harvest, or scheduling a holiday, we rely on an ancient translation, forcing the universe's messy fractions into a perfect human rhythm.